Welcome to The Explainer. So how does a machine actually learn? I don't mean just memorizing stuff, but really learning to make a smart guess, a prediction about something it's never seen before. We're going to break down that exact process. And you know what? It all kicks off with a surprisingly simple question.
All right, so let's start with a classic problem, something we can all wrap our heads around: predicting house prices. This is the perfect example for getting the core logic of machine learning. The very first thing we're going to need? Data. Lots of data to learn from.
Okay, so we feed the machine what's called a training set. In this case, it's just a simple list of real houses from Portland, Oregon. You can see we've got their size in square feet and what they actually sold for. The machine's entire goal here is to just stare at this data and figure out the hidden pattern, the relationship between a house's size and its price.
Right, so if you or I looked at this, we'd probably spot a trend pretty quickly. Bigger house, bigger price, right? But for a machine, the whole learning process kicks off with a really simple, almost elegant idea. It tries to draw a line. That's it. Because if it can find one single straight line that best fits all these data points, well, then it can use that line to predict the price of any new house, just from its size.
And this line, this is what we call the machine's model. In the world of machine learning, you'll hear it called a hypothesis. It's basically the machine's best guess, its theory about how the world works, based only on the data it's seen so far. Okay, so you see this formula on the screen, and I know what you're thinking: math. But don't worry, don't let it scare you off. This is just the basic recipe for a straight line. The only parts you really need to care about are these two little symbols, theta 0 and theta 1. Just think of them as a couple of dials, right? Dials the machine can turn. As it turns them, the line moves up and down, and its angle changes. It's just twisting these dials to try and find that perfect fit. But, okay, that leads to the big question, right? How does the algorithm actually know which way to turn the dials? I mean, there are literally infinite possible lines it could draw. It can't just eyeball it like we would. It needs a totally precise way to measure how good, or more importantly, how bad, any given line is.
And to do that, to give it that measuring stick, we bring in this really important idea called a cost function. You can think of it as the machine's own personal scoring system.
So here's what it does. For any line the machine tries out, the cost function looks at how far away that line's predictions are from the actual house prices in our data. It measures the gap, the error. So a line that's way off from the real data points, boom, it gets a really high error score. But a line that slices right through the middle of the data, getting super close to all the points, that one gets a very, very low error score.
And suddenly, this big, abstract idea of learning just boils down to something super simple and concrete. Find the dial settings that give us the lowest possible error score. That's the whole game. The entire process is now just a hunt for the minimum error. So the next question is obvious. How does it actually do that hunt?
This is where things get really cool. To actually find that minimum error, we use this incredibly clever and powerful algorithm called gradient descent.
Honestly, the best way to get your head around gradient descent is to not think about math at all. Let's use an analogy. Imagine that all the possible error scores form a giant 3D landscape. High error scores are like the peaks of tall mountains, and low error scores are the bottoms of deep valleys. Our one and only goal? Find the absolute lowest point in that entire landscape.
So how do we find the bottom of the valley? You might think it involves some crazy complex math, but the answer is way more intuitive than that. We just tell the machine to, well, take a walk. It really is this simple. The algorithm starts at some totally random spot on that landscape. From there, it looks around in every direction, 360 degrees, and figures out which way is the steepest path downhill. Then, it takes one tiny step in that direction, and then it just does it again. Look around, find the steepest way down, take a step. Look, step, look, step. It just keeps repeating this simple little process until it can't go any lower, until it's standing at the very bottom of the valley. That's it. That's the point of the lowest error.
Okay, but there's a really critical detail here. How big are those steps it's taking? In machine learning, we call this the learning rate. And trust me, getting this one parameter right is absolutely crucial.
Because think about it, if your steps are way too small, yeah, you'll eventually get to the bottom of the valley, but it's going to take forever. It's just super inefficient. On the other hand, if your steps are too big, you might just leap right over the lowest point and land on the other side of the valley. And if you keep doing that, you might just bounce back and forth forever, never actually finding the real answer.
So, What's really interesting is that there's not just one way to do this whole walking downhill thing. The algorithm can actually use a couple of different strategies for its journey, and each one has its own pros and cons.
Yeah, let's stick with our hiker analogy. First, you've got batch gradient descent. This is the super careful, methodical hiker. Before taking even a single step, it stops and looks at every single data point we have, every house, to calculate the absolute perfect downhill direction. It's incredibly precise, but as you can imagine, it's also incredibly slow. Then you've got the other type, stochastic gradient descent. This is the energetic, maybe slightly chaotic hiker. It just looks at one house, takes a quick step, then looks at the next house, takes another step. It's way, way faster, but its path to the bottom is a lot more wobbly and indirect. But when you're dealing with big data, millions or billions of examples, that speed is absolutely essential.
So when you boil it all down, learning for a machine is this really elegant three-part dance. First, you define a model. For us, it was a simple line. Second, you create a cost function, an error score, to measure how good that model is. And third, you use an algorithm, like gradient descent, to systematically hunt for the model that has the lowest possible error. That's the core loop.
And don't let the simplicity fool you. This quote from Andrew Young at Stanford really hits it home. This fundamental idea, linear regression with gradient descent, is still one of the most widely used algorithms in the world. It's the absolute bedrock for so many of the complex, intelligent systems we use every single day.
So, okay, we've figured out how a machine learns when the answer is a straight line. But what happens when the real world is more complicated? When the relationship isn't a straight line at all, but a curve? Well, asking that simple question opens up a whole new universe of possibilities. And that's the next critical step to understanding how machines truly learn.